Hello toppers, today we are going to analyze very important concepts related to analog to digital converter, means ADCs. And we are also going to analyze the various experimentations related with the analog to digital converter. So let us start. So let us begin the analysis of ADC from this diagram, where this diagram suggests the input to this ADC is analog input, means the input is in analog form, whereas the output is in digital form, consisting of binary bits, that is 0 and 1. Okay, means the input is in raw form or analog form, and the output is digital, means it comprises of zeros and ones. Okay, so this is the basic setup of experiment which we are going to analyze in this session. So let's be in this session. We are starting the session with the basic definition, means ADC is a circuit. ADC is a circuit that converts continuous signal, that is analog signal, into binary value. Binary value means digital value. So that device, that circuit which converts analog value into binary value is called an analog to digital converter, ADC. Okay. So in this analysis, you must know what are the steps that are involved in converting an analog signal to digital signal. So steps which are involved in converting an analog signal to digital signal are: the first process is sampling and holding. The process of sampling and holding involves the band limiting of the analog signal, means settling some periodic sampling points and freezing the analog signal at sampling points so that the signal does not change for the duration of conversion. So the process of sampling and holding is an important primary step for the process of analog to digital conversion. The next process is quantization. So quantization means the determination of what digital value is best representing the analog signal level. Okay, and the next step is encoding. This encoding involves the method of assigning a digital equivalent to the sampled signal. Okay, so why this is done? These processes are done to ignore sudden changes in the analog input, and in this sampling, various theorems like Nyquist sampling theorem can be used to determine the sampling periods. Also, Volvano postulate can be taken care of while sampling the analog signal. And this quantization and encoding, these are the processes which are included in the conversion of analog signal into digital signal. So if you'll see some basic example where this analog to digital conversion is needed, one basic example you can consider is of your smartphone. Means if you are having a smartphone, at the place of microphone, whatever you are speaking, that signal is analog signal which is being fed to the ADC present here as analog input. So whatever you are speaking at the microphone of this phone is getting carried to the ADC present, and that ADC converts that analog signal into digital signal, and it sends that digital signal to transmitting unit to transmit that digital signal. Okay, and this is the transmitting unit. So what happens at the receiving unit, that this digital signal is received by this receiver, and that digital signal is converted into analog form by DAC, digital to analog converter, and that is given back to another phone which is present at the receiver side. Here this transmitted digital signal gets converted to analog form, and the second user receives the analog signal. Whatever message was being conveyed, that is getting received to this receiving unit. So one important parameter you can note, that the resolution of this analog signal is infinite. The resolution of this analog signal is infinite. So one question arises now, that why there is a need of analog to digital conversion? What is the problem in analog signals? So few points you can consider: that analog signals are susceptible to noise. It is difficult to process signals in analog domain, and also it is difficult to store signals in analog domain. So there is a need of conversion of that analog signal into digital domain, and that digital signal is less susceptible to noise, and that digital signal is easy to process in digital domain, and also digital signal is easy to store in digital domain. So there's a need of conversion of analog signal into digital signal. So now let us have a look upon the types of ADCs. The first type is counter type ADC. It is also called as staircase ramp type ADC or ladder network type ADC. So here the advanced version of this counter type ADC is successive approximation register SAR-type ADC. The next type is parallel comparator of flash type ADC, and the next type is dual slope integrating type ADC. Some other types of ADCs also include sigma delta ADC and pipeline ADC. Here this parallel comparator of flash type ADC is the fastest ADC, and this dual slope integrating type ADC is the slowest ADC, but it is most accurate. Here this is a diagram of counter type ADC in which a counter is used to count the number of clock pulses to provide binary outputs. You can see here. And here a comparator is used to compare input analog voltage with reference voltage generated by the DAC in feedback. So here what happens that when the analog voltage, the input analog voltage VA is greater than the reference voltage, and then the counter will show the increment by 1, means basically it is an up counter. And this comparator works on the principle that whenever the applied quantity on the positive terminal is greater, the comparator gives the high output, and whenever this VA, let us suppose this feedback value is VB, so whenever VA is less than VB, then the comparator output will be 0 and the clock pulse is not applied to the counter and the counter will stop. So at this time, the counter will represent the binary equivalent of the analog input voltage. So here in counter type ADC, the conversion time vary with the input analog voltage, and here maximum number of clock pulses required for n bit conversion is equal to 2 raised to power n minus 1. Means if it is a 4-bit counter type ADC, then number of clock pulses required will be 15 clock pulses. And why its name is called a staircase ramp type ADC or ladder network type ADC? Because whenever you will plot its output, suppose this is the analog input and this is the binary output. Means x-axis is representing analog input 0, 0.5, 1, 1.5 like that in volts, and it is 0, 0, 0, 0, 0, 1 like that. So whenever you will be plotting this analog value versus digital value, digital output, you will be getting the plot like this, something like this. So this is representing a ladder network or staircase ramp type. So it is called a counter type ADC. So such type of output will represent that resolution of this counter type ADC is somewhat greater. Means the step size between different convergence sequences are more than that of more accurate type of ADCs. Now let us have a look upon the experimentation part of this counter type ADC. Let us now connect the power supply to this ADC kit. And this power button of this ADC on. Now let us begin the discussion for this 4-bit staircase ramp type ADC. Means this is basically a counter ADC where the positive terminal of the comparator is fed with analog input. This knob is used to provide analog input to this comparator's positive terminal so that this comparator compares this analog input with the digital output converted into analog form as a feedback. This comparator compares the analog input with the digital output converted back into analog form at its negative terminal. So let us turn on this multimeter. You can see this multimeter has been turned on, and now we have to apply the input at the input terminal of the comparator. This patch cord is connected at the input supply, and this will be fed into the positive terminal of that comparator. So this input supply has been given to the comparator's positive terminal. Now we can take the readings correspondingly. For taking the readings, we are taking the positive terminal of this multimeter and connecting it to the input supply, and another terminal of this multimeter I am going to connect it in the ground of this kit. So this ground terminal has been connected, positive terminal has been connected, and now we can take the corresponding readings. This switch has been brought to reset position. So we are considering the case of a 4-bit counter type ADC, and we can take the corresponding readings of all the 16 voltage levels. Means there can be a possibility of 16 observations, and we are going to take every observation for this 4-bit counter type ADC. Okay, so let us start. Here I am bringing this switch position from reset to count, and now here we can see all the LEDs are not glowing. Means D0, D1, D2 and D3 all are zeros. We are starting to increase the analog input. So by rotating this knob, we can increase the analog input that is being supplied to this comparator's positive terminal. So we are increasing. So here we can see the first LED, the D0 input has turned on. So this D0 is now switched to 1, and this D1, D2, D3 all are 0. 0, 0, 0, 1. This D3 is MSB, most significant bit, and this D0 is LSB, least significant bit. So here we can consider this output as 0, 0, 0, 1. So corresponding to this 0, 0, 0, 1 output, we have supplied the input of 25.6, almost 25.6 millivolts. Here you can see in the multimeter. Now when we will increase this input, now the condition for output has changed. This is the case for 0, 0, 1, 0. Now we are increasing again, and after increasing you can see again the change state of the output changed to 0, 1, 0, 0. Again I am increasing from this knob, and you can see the output state is 0, 1, 0, 1. Again I am increasing. So you can see the output state is 0, 1, 1, 0. Now again I am increasing. You can see the state of the output is 1, 0, 0, 0. Again I am increasing, means 1, 0, 0, 1. Now I am supplying the maximum input to this comparator's positive terminal, and we can see all LEDs are glowing. Means the output state is 1, 1, 1, 1, and this maximum voltage is coming corresponding to the input 5.13 volts. For a 4-bit counter type ADC, I am considering this set of data which has been taken by one of my random students in IIT. So some basic parameters which we can find from this set of data. We can find out the range of the voltage of this 4-bit counter type ADC. That is, we can find this range by Vmax minus Vmin. Means the maximum voltage level minus minimum voltage level gives the range of this 4-bit counter type ADC. This parameter V range can be found out by this maximum voltage level 5.13 minus minimum voltage level 0.7 millivolts. So 0.7 into 10 raised to power minus 3 volts. So upon calculation, we will find the value to be 5.129 volts. So the range of this 4-bit counter type ADC is 5.129 volts. Now, if we want to find the resolution of this ADC, it can be calculated by V range upon 2 raised to power n. N is the number of bits. Since we are considering a 4-bit counter type ADC, so n will be 4 here. So we can calculate this by 5.129, the range of the voltage, upon 2 raised to power 4. So when we will calculate this, we will get the value to be 0.32. So this is the resolution of this 4-bit counter type ADC corresponding to this dataset. We can also find maximum quantization error. So it can be calculated by resolution upon 2 plus minus resolution upon 2. So its value will be plus minus 0.16. Now you can take a note point that you can calculate percentage resolution by using a common formula which is valid everywhere. So for this case of 4-bit counter type ADC, we can calculate the percentage resolution to be 1 upon 2 raised to power 4 minus 1 into 100, which can be calculated to be 6.67%. So the advantages of this 4-bit staircase RAM type ADC is that it is simple, it is easy to design, and it is of low cost. But it is not used where high precision is required. Where high precision is required, we switch to the 8-bit successive approximation register type ADC. So here it is just an advanced version of the previous staircase RAM type ADC, where the number of clock pulses required is reduced to n. Here the number of clock pulses required was 2 raised to power n minus 1, means for this case 15 clock pulses was required. But here, though the analysis of this voltage level signals is increasing, the number of clock pulses required is getting reduced to 8, means n number of clock pulses is required for conversion. Means to reduce the conversion time or to increase the speed of operation, we are switching to this advanced version, means 8-bit successive approximation ADC. So we can take corresponding readings of this counter type ADC and SAR type ADC. So we will supply this input now to this 8-bit SAR type ADC. Here you can see, and I am making this 4-bit ADC to reset. And this analog input I am making to 0. So you can see this is a simple schematic of 8-bit successive approximation register based ADC. So we have applied that input to the input terminal of this 8-bit SAR type ADC, and we will correspondingly observe this output of 8 bits. So whenever I have made this input to 0, means all the output terminals are 0. So ignore this LED blinking, this is due to an error. So whenever all these LEDs are at 0 output, we have an input of 0.7 millivolts. You can see here. Note that this D7 is the most significant bit and D0 is the least significant bit. So correspondingly you can get the outputs. The LEDs which are glowing is treated as 1 and the LEDs which are not glowing is treated as 0. So in this case of 8-bit SAR type ADC, the total number of readings we can take is 2 raised to power 8, means 256 readings we can take. But it's hectic to take all 256 readings. So I am taking just 16 random readings to show you just its overall working. Whenever I have applied the maximum input, all the LEDs are glowing and corresponding reading is 5.44, almost 5.44 volts. Now let us consider this set of data for 8-bit SAR type ADC. So here we can also calculate this V range by subtracting Vmax minus Vmin. So here Vmax is 5.44 volts and Vmin is 0.7 millivolts, means 0.7 into 10 raised to power minus 3 volts. So that will give 5.439 volts. Now you can calculate the resolution by using the same formula, VR upon 2 raised to power n. So VR here is 5.439 and the number of bits here was 8 bits. So 2 raised to power 8. So you'll get the value of resolution as 0.021. And you can also calculate the maximum quantization error, that is plus minus resolution upon 2. So here the maximum quantization error is 0.021 upon 2 and that will be equal to plus minus 0.0106. Here you can also calculate this percentage resolution by using this formula 1 upon 2 raised to power n minus 1 into 100. So for this 8-bit SAR type ADC, this percentage resolution will be 1 upon 2 raised to power 8 minus 1 into 100. That will be 0.392%. So here you can see the value of resolution in case of 8-bit SAR type ADC is lesser. So here in this SAR type ADC, the speed is improved and the accuracy is improved. So if you can see, there is a major drawback in the case of 4-bit staircase ramp ADC. Like this counter in the circuit has to reset in every conversion sequence, means it is slow. Means this 4-bit staircase ramp type ADC is slow in comparison with this 8-bit SAR type ADC. Here there is no concept of counter. One SAR is there, one successive approximation register is there, and the conversion takes place just sequentially. You can see whenever I am increasing, sequentially the output sequences increase. But whenever you will see in this case of 4-bit staircase ramp type ADC, if it is the first conversion sequence, then for going to the next conversion sequence, the counter resets, means this D0 LED will turn off and then another conversion sequence will appear. So you can see that. Means during each conversion sequence, this counter resets and ultimately the conversion process is slow. Now let us move forward to another type of ADC. So here it is the sample diagram of the next type of ADC, that is parallel comparator ADC, or it is also called as flash type ADC. It is the fastest among all the ADCs. This fastest means it takes the minimum number of clock pulses for the conversion. So here the maximum number of clock pulses required for the conversion is only 1. Now if you can see this diagram, this is a 3-bit flash type ADC. Here B0, B1 and B2 we are getting as digital outputs, and one reference voltage, that is Vref, has been applied to this combination of registers, and there are several comparators and one priority encoder. So here as per the voltage division rules, the voltage is getting divided at every nodes. So here the voltage will be 7 upon 8 Vref, because there are 8 resistances. Here at this node the voltage will be 6 upon 8 Vref. Here 5 upon 8 Vref. Here 4 upon 8 Vref. Here 3 upon 8 Vref. Here 2 upon 8 Vref. And here 1 upon 8 Vref. So this much voltage is available at every nodes. And here this is a 3-bit flash type ADC. So 2 raised to power 3 minus 1 comparators are required. Means this much of comparator is required just for 3-bit conversion. So this is a drawback of this flash ADC, that just for the 3-bit conversion, the number of comparators required for conversion is very large. So that is the drawback. And here few important points you can note for this parallel comparator or flash type ADC is that for n bit, the number of comparators required is 2 raised to power n minus 1. Number of registers required is equal to 2 raised to power n. And number of priority encoder required is 2 raised to power n into n. So now let us move on to the next type of ADC, that is dual slope integrating type ADC. Here it is most accurate but slowest ADC. Here you can see in this diagram that integrating portion is present, and here all the ripples and noise is separated or compressed by this capacitor. Therefore, this type of ADC has more accuracy due to this integration process. So here the maximum number of clock pulses required for conversion is equal to 2 raised to power n plus 1. So here you can see at this switch, one analog input is provided and another reference voltage is provided as a feedback from this control circuit. So there are two processes involved. One is integration and another one is de-integration. So this integration time is fixed period of time. Let's call it Ti. And this de-integration time is dependent on input. So here the expression for this analog input can be written as the integrator's output minus 1 upon RC into Vin into this integration time. So here an expression for analog input can be written as minus 1 upon RC VA into Ti, this integration time. So this integration time here will be like this, means up to Ti the slope is negative, and in the de-integration time the slope will be positive. So by adding this integration time and de-integration time, we can write minus 1 upon RC into VA into Ti plus the reference voltage VR into TD upon RC is equal to 0. So from here we can write V input into this integration time Ti is equal to V reference into D integration time TD. So from this expression we can write a relation between the analog input with integration time and de-integration times, that is V reference into TD upon Ti. So that is the relation. So now let us see some more types of ADC which has been more popular in recent times. So that is sigma delta ADC. The sigma delta ADC is a high resolution, high speed, low operating voltage and therefore a low cost ADC. And the various applications where the sigma delta ADC is used is in digital audio series, in codec, in biomedical sensor applications, and in wireless transmitters or receivers. Now one more important type of ADC is pipeline ADC. Here multiple low resolution stages are cascaded and the direct digital measurement technique is used for its operation, and these are mostly found in the smartphones, in mobile phones nowadays. So this was all about ADCs. Thank